Good afternoon, everyone. So it is my pleasure to welcome you to this new event or appointment of our 40 under 40 lecture series on combustion. Today, I have the great pleasure to welcome Professor Matteo Pelucchi from Politecnico di Milano. So Matteo obtained his PhD in industrial chemistry and chemical engineering at Politecnico in Politecnico di Milano in 2017. Since then, he has been assistant professor of theory of and development of chemical processes at the same institution. During the years, he has been a visiting scholar at different institutions. In 2012, he was in Galway and Ireland. In 2016, he was in Argonne National Laboratory, and is currently visiting professor at Tongji University in China. His research activities covers the development of detailed and semi-detailed chemical mechanisms for several processes that are relevant in the context of decarbonization and circular economy. Beyond the sustainable fuels and combustion, he also works in the areas of waste recycling, plastics and biomass, but also pyrolysis and gasification, and also in the field of turquoise hydrogen production, and as well as in carbon materials from hydrocarbon cracking. So without further ado, I would give the word to Matteo, thanking him again for having accepted our invitation. Thank you.
Thank you, Alessandro. I'm sharing my screen. I believe you can see it. Good presentation mode. Okay, first of all, I would like to thank Alessandro, Salvatore, and Ward for organizing this lecture series. I think is very important to give room to, let's say, younger generation, even if not that young anymore, of scientists. And it is my pleasure to give my contribution to this lecture series. So the title of my presentation is Chemistry Models for a Circular Economy, and I'll be talking mostly about two examples that I've been dealing with together with many people in the group, of course. One is plastic waste recycling, and one is turquoise hydrogen and carbon materials production. So I'm not exactly talking about combustion in this context, but I'm talking about pyrolysis, which is, as many of you know, of course, propedeutical to understanding combustion, even at high temperature. But I'm talking about pyrolysis for other scopes, not within let's say, a combustion process itself. First of all, a bit of introduction of the group. The CREC Modeling Lab in Milano, we're strictly a computation and modeling group. I believe many people in the staff, including Professor Faravelli, which is the head of the group. And I have also many PhD students, and in particular, I reported in blue those significantly under 40 scientists, researchers, PhD students, where I stole material basically from their results, as they are, of course, leading the research topics I've been talking about. In terms of acknowledgement, so we get this out of the way. On the side of thermochemical recycling of plastic waste, we are now involved in a European Union project called Electro that is led by the University of Ghent, Professor Kevin van Diem, that is also very active in the area of thermochemical recycling of plastic waste, and partly by Eni, the Italian oil and gas company. On the side of hydrocarbons cracking for hydrogen and carbon materials production, in this context, we work very closely, collaborate with another big group in Politecnico di Milano, which is the Laboratory of Catalysis and Catalytic Processes. Most of the support is coming from a consortium, Carbon Hub, which is based at Rice University and led by Matteo Pasquali. We also recently were awarded a PRIN project from the Italian Ministry of University and Research. And the industrial applications I've been talking about mostly are in the context of a collaboration with Brembo, a leading company in braking systems production. Okay, so I would like to talk about, let's say, to some extent, how we are trying to apply what we learned in terms of methodology and workflow in the area of combustion kinetics, where I think the community, particularly in combustion kinetics, has reached huge advances since I started to work in this area back in 2012 or so. We're really covering by means of advanced experimental measurements and advanced computational techniques and theory. We're really working closely together with the aim of reconciling theory experiments and modeling efforts. So if we look at these in a multi-scale perspective, so we start from a molecular reaction scale modeling. What we are typically aiming for, and in combustion kinetics, again, we're pretty familiar with this, is trying to figure out what are microscopic experimental targets that through which we can isolate purely chemical kinetics phenomena or purely heat and mass transfer phenomena. But let's talk about chemical kinetics mostly. So if we are able to isolate a system, a reactive system, so that we get rid of any heat and mass transfer limitation, we're focusing on kinetics, then we can couple these with the theory approaches, potential energy surface exploration, ab initio transition state theory, master equation, and so on, and start to develop detailed and semi-detailed chemistry models. Of course, the topics I'll be talking about today are slightly different compared to combustion, which is mostly an homogeneous phase if you talk about gas phase, or to some extent liquid phase, fuels combustion. I'm talking today about some multi-component and multi-phase processes, thermal processes, such as plastic recycling and carbon and hydrogen production from hydrocarbons cracking. But the approach could be the same. So once we have identified what is the kinetics, we can develop detailed and semi-detailed kinetic models, and then we want to validate these kinetic models by means of comparison with 0D and 1D reactors. Then maybe we have some loop to improve our kinetics understanding and description. And then once the model are able to predict these experimental targets, we are able to use them in CFD reactor scale simulations. So in the blue box, you see the experimental parts of the approach, and in the white box, you see the modeling parts of the approach. To do so, in Milano, we develop many different tools in-house, in particular led by Professor Quaci activity. And even by developing these tools, we cover the same scale. So we start from molecular scale understanding by using automated tool for potential energy exploration and rate constant computation. Then we develop the chemistry models. Some of them are automatically generated. Then we can make model reduction to make them applicable to CFD calculations. Also, we have our OpenSmoke++ framework that I hope many of you are familiar with. And then we rise up until 2D and 3D types of simulation setup. These are all free for academic and educational purposes, so feel free to reach out in case of any of you is interested in using any of these tools. At the core of our research is the chemical kinetics framework. The chemical kinetics framework is modular, hierarchical in structure, and is modular also in the sense that we can couple heterogeneous type of processes to gas phase homogeneous processes. And in particular, what I've been talking about today is two examples: chemical recycling, solid plastic waste, and turquoise hydrogen and carbon materials production. And you see in this figure how they connect, and I will explain the reasons. Some are obvious, some are maybe less obvious to some of you, to connect these modules, these heterogeneous modules, to the main mechanism which describes the gas phase evolution of species. If we think about the energy scenario, everybody has understood how much integration is needed to achieve the sustainable development targets, the decarbonization in the energy and in production industry, and to implement in the industry circular economy principles and concepts. So at the core of this picture that I stole from Tiziano is hydrogen. Hydrogen is foreseen as the carbon neutral energy vector and fuel for the future. And the assumption in this is basically that we will be able, and we will, to produce hydrogen from water electrolysis by exploiting renewable energy sources. This is not the only way to produce hydrogen. What I've been talking in example number 2 is another opportunity that we have, which is converting natural gas or in general hydrocarbon feedstocks into carbon materials and hydrogen. And based on the value of the carbon materials, the value of hydrogen will decrease and will become competitive with, for example, steam methane reforming processes, which right now dominate the hydrogen production market. And the example number 1 is instead still connected to this fully integrated energy scenario, which is the capability of recycling waste. And waste can be plastics, can be biomass, can be a mixture of those, can be waste from new processes that we are developing in the context of decarbonization. For example, if you think about anaerobic digestion to produce biogas and biomethane, maybe you have some sludges that are kind of dirty feedstocks that you want maybe to recycle or maybe upcycle them to something that is valuable. The core building block in this, if you think about gasification, would be syngas, as syngas allows you to basically access the entire chemical industry. But if you're not interested in syngas, maybe you can increase the hydrogen yields and then produce hydrogen as a fuel. In this plot, you see gasification. I'll be talking about pyrolysis, but again, same as in combustion, pyrolysis is propedeutical to gasification. So when you have a solid fuel as these cracks and volatiles in the solid phase or in some sort of liquid phase, and then the fragments comes up and maybe they get partially oxidized in the so-called gasification process. So example 1, plastic waste recycling. How big is the opportunity of plastic waste recycling? So if we think about European Union data, out of the nearly 30 million tons per year that are collected in the EU, roughly 8.5 million tons are either landfilled, mismanaged, or lost in oceans. Just to have an idea of the quantity of these, at some point I made some stupid calculation as I wanted to see how big this issue was. And then I realized that if I took the Isozaki Tower that is located in Milan, actually pretty close where we will have the Combustion Symposium, right in front of the conference center where we will have the Combustion Symposium in July. So you're all invited to come. The deadline is, I believe, in 1 month time. So if you make this calculation, all of a sudden you realize that these 8.5 million ton a year of mismanaged or landfill waste can fill about 34 of these skyscrapers, which are 20 by 15 meters and 200 meters high, which is something very impressive. What is this plastic waste mixture we're trying to recycle or upcycle? It's a mixture of many different polymers. It changes in space and time. And this is one of the reasons why we need to model the chemical kinetics of this, because if we are able to characterize the feedstock, maybe we are able to make some prediction of what the output of a reactor doing pyrolysis or gasification will be. So if you take this composition, and again, doing some simple maths, you consider the heating value that you obtain from the weighted sum of the relative percentage of each polymer into a typical plastic waste mixture. All of a sudden you realize you could be able to produce something like 10 to the 11 megajoules of energy, which is the demand of 13 million people, which is probably about the size of the biggest cities in Italy all sum up. So it does not cover the demand for the entire European Union, but at least is some sorts of fuel and energy, if not of new plastic polymers that you can produce with chemical recycling. What is done so far with plastic waste? Well, 42% in the European Union are converted through energy recovery, which is a mature technology. You can get to high efficiency, combine heat and power up to 60%. Is feed flexible. You can feed whatever you want. You get a 90% mass reduction. You're left with ashes and maybe some solid char residue. The problem is that they produce emissions, maybe also dioxins, if you think about PVC being included in this plastic waste mixture. And it has no priority in EU circularity plans. As you see in this triangular plot here, energy recovery is right above landfill disposal. So there's no priority in this. The other thing we're doing, and things are also improving in this sense, is mechanical recycling. So this is actually recycled. It's good for uncontaminated feedstock. You can take a waste of polyethylene, polypropylene, styrene, and so on, separate them and mechanically recycle them, basically grind them down to pellets, and then resend to polymers producer or packaging producers, and they can reuse this. It has some counterpart, complexity and cost of pretreatment, the degradation of polymer properties by after a few cycles of mechanical recycling is not an upcycling. You can obtain polyethylene from polyethylene. And is not applicable for multi-layer packaging materials, which are actually the main problem as the, for example, if you think about food packaging, these are typically multi-layers of many different polymers, and you don't see the layers, so it's even by view, you can imagine how costly it could be to separate these layers into single polymers and then apply mechanical recycling. Chemical recycling so far is covering only 0.2%, so 0.06 million tons per year. There are forecasts, though, that, for example, from McKinsey or from Vollmer and co-workers, some recent study, that foresee how the thermal recycling, thermochemical recycling of plastic waste will increase by 2030 from less than 1%, as we just saw, to about 13%. What are the features of thermochemical recycling? And with thermochemical recycling, I mean both pyrolysis and gasification. Well, the features are that it converts waste to new feedstocks, monomers, fuels, hydrogen, syngas, is probably the only route for heterogeneous, variable, and contaminated feedstocks, such as multi-layer packaging material. It is an upcycling process. If I make syngas, I can then make methanol, I can make olefins, and then I can make a brand new polyethylene, propylene, or polyolefin of any kind. Gasification, if properly run, is autothermal by balancing the reforming reaction, endothermic, and the partial oxidation reaction that are exothermic. The issues are that pyrolysis requires heating of a solid / liquid when it melts media. So, you know, CP is different from gas phase properties are different. So it's hard to get at the core of a reactor with suitable heating. The dependence of product distribution on feedstock and condition is, of course, something that needs to be understood. And we hope that through our model, we can help out with this task. Is a multi-phase and multi-component process. In gasification, for example, there are many other challenges like reactor clogging due to agglomeration phenomena. And as I said before, for energy recovery, emissions could be a big problem also in gasification systems. This is how a multi-layer packaging material looks like. So you have layers of polyethylene, polyethylene terephthalate, polyamides, so nylon, and some other specialty polymers. Every layer serves a scope, so oxygen barrier, and so on. So this is a quite complex material to be recycled. What is the value chain at downstream of pyrolysis? So you get your waste, you do cleaning, drying, and sizing. You want to feed it to a pyrolysis reactor. You will get some char residue. There are 3 phases in pyrolysis: tar, gas, and char. You do some purification and upgrading. You get an oil fraction that you can distill. You get a gas from the head. You get a naphtha from in between, and you get some heavier fuel from the bottom that you can upgrade and make fuels from plastics. If you can take gas and naphtha, then you can send them to a steam cracker and you produce monomers. And once you have monomers, you can make polymerization again and you close the loop. Gasification is kind of similar in the pre-treatment. Probably you don't need to get rid of water content because that might be helpful. You get into your gasifier, you produce syngas. If you want to increase the hydrogen yields, you make a water gas shift reaction. And this provides hydrogen. Otherwise, you can live with syngas. You can target a certain CO to H2 ratio, and maybe you can make ammonia. You can make urea, so a fertilizer, by also using CO2. You can make fuels from Fischer-Tropsch. You can make methanol from syngas and from methanol olefins, and then polymers again. So this is a 1-year-old right now article on chemical engineering use. And since then, I've seen an explosion in the literature of studies on plastic waste pyrolysis and gasification. And there are different scales, as I said before. I'll be focusing on, let's say, the micro scale, on the chemical kinetics aspects, but that's not all. There's molecular diffusion to be taken into account. At the mesoscale, you have phase transfer between a gas and the liquid. You have a bubbling type of system. You have convection, solubility issues that I've been touching upon. And then you get at a macro scale where you have temperature and concentration gradients, reactor impeller design challenges, and heat management, like I said before. So can we solve the key challenges of, or some of the key challenges of thermochemical recycling with multi-scale modeling of chemical reactors? Why I'm talking about pyrolysis? Well, first, because it's an interesting process, and second, as I said already, is because it's propedeutical to many other processes like catalytic pyrolysis, gasification, catalytic gasification, or even combustion of solids. So when you heat up a solid fuel, these cracks into light gases and condensable gases, or TAR, what it's called as, usually referred to as pyrolysis oil. And if you give time for these species to evolve, of course, temperature and time, there are secondary gas phase pyrolysis reactions that happen. In the case you're doing gasification, instead you're feeding water and oxygen, or water and air, to achieve those autothermal conditions. And you have also secondary gas phase reaction, but this time are oxidation reactions. On the side, on the solid part, on the char that is left, you are able actually to consume this by heterogeneous char oxidation reactions. And these are, let's say, single-step type of reactions that are typical of gasification systems. So, as I said before, the balancing between steam reforming and partial oxidation, one is endothermic, one is exothermic, allows you to reach autothermal condition. I'll be focusing, though, more on the red box, on the pyrolysis chemistry of solid plastic waste pyrolysis. So, as I said, the main objective would be to get the product distribution right. So if I feed a certain feedstock and I operate the reactor at a certain temperature, pressure, residence time conditions, what am I getting as a product? So I plotted here a few data that I collected in the literature in a slow pyrolysis, very high residence time, over 1 hour, relatively low temperature, 450 degrees. If you start from pure polymers by looking at the split between the oil fraction, gas fraction, char, and waxes, you see polyethylene, propylene, and styrene behave very differently between one another. If you increase the complexity, if you zoom in on the oil fraction from polystyrene, of course, you're expecting a lot of styrene to be produced, but then other alkylated aromatics also come up contextually. If you increase the complexity of this mixture, so you move to binary mixtures. So let's take polystyrene now with polypropylene. The oil fraction has dramatically decreased by 4 times, and the products you're forming are also very different. You still have styrene, you still have ethyl benzene, but now you start to have some alkylated aromatics and like, for example, propyl benzene, alpha methyl styrene, and so on. If you move on to ternary mixtures now, so polystyrene, propylene, and ethylene, the things become more and more complex. Imagine then if you also increase it in terms of complexity, and you also introduce a polymer that has some additional heteroatoms that are not only carbon and hydrogen, like polyethylene terephthalate, and you can all of a sudden go crazy in understanding what the products and how complex the product distribution is that is coming out from these polymers. And you also start to see some effect of impurities, like these silica containing compounds that were measured, that may be coming from anywhere, actually. About the rampant approach to solid plastic waste pyrolysis that we have developed at CREC, the objective is exactly what I said before. It's like you're doing a cake and the ingredients keep changing all the time, and the cake should taste the same, or at least good, anytime, independently of what the ingredients or the source of ingredients is. So we're developing a kinetic subset for a palette of polymers, polyethylene, propylene, styrene, PVC, PMMA, PET, polyamide, and polyurethanes are under development. There was a first fully detailed kinetic models that were published back in the late 90s by Ranzi and Faravelli and co-workers. They were actually fully detailed, so we're talking about millions of species, so not applicable CFD, not probably even in model reduction tools. Then in 2007, Maronjo and co-workers came up with the first LAMP model for PVC pyrolysis, The same approach has been applied to biomass from 2007 to currently. And then Andrea took over, a PhD in our group, PhD student in our group, Andrea Locaspi. And since the start of his PhD, he started to generalize and make more rigorous this lumped approach, and he applied it to polyethylene, propylene, styrene, and is working also on the other polymers that I mentioned before. There are a few papers from him that are already published, and you can find them in the literature. We also published together with Kevin Van Giem group, I think a nice review paper 3 years ago on the chemistry of chemical recycling that I invite you to look at. It provides a nice overview of the different approaches in terms of kinetics modeling and also heat and mass transfer modeling. So what is this lumped or functional group approach? So let's take a polymer, is a long carbon chain backbone with different functional groups. The functional groups change between polyethylene and polypropylene. One as a H as a functional group, one as a methyl, polystyrene as a aromatic ring, PVC as a chlorine molecule. The main interest, let's keep this in mind, is, and the advantage probably of a semi-detailed kinetic approach is that we can come up with a product distribution. Of course, it won't be fully detailed as we're not tracking each single carbon atom in the polymer chain backbone, but we're talking about functional end chain and mid chain functional groups, moieties, let's say, in black and red, respectively, in this case, that cover between C20 and C40 in terms of size of the molecule. Why C20, C40? Because if you think about heating up a polymer, these cracks, and if you form a species that has, let's say, roughly a carbon number of 40 or below, this species at those temperatures will probably evaporate in the gas phase. And so we need to track that species evolution then in the gas phase by connecting that to our gas phase model. So in general, we have different chain lengths. So the polymers in a polymer mixer are not all the same length. You can think about a Florey-Schultz distribution. But basically, they all have the same repetitive units. They are just different amount of mid-chain groups and end-chain groups. Then the end-chain groups can be a primary carbon atom, can be a vinyl type carbon atom, as you see in this graph here. What are the reaction classes that govern the pyrolysis of the species? They are the same that govern the pyrolysis of, let's say, N-decane in the gas phase. So we have random scission, what we call initiations in the chemical kinetics community, or radical recombination. This, of course, can go back. You form a radical. This radical can isomerize, and this backbiting reaction have a huge impact on the product distribution. Or you can form a radical from the chain backbone of the polymer by doing an H abstraction. So you're forming, in this case, an high molecular weight mid-chain radical. This decomposes by beta scission. All of these fragments can again decompose, can isomerize, can recombine with radicals. The reaction classes are well defined: random scission, beta scission, H abstraction, unzipping, recombination reactions, and so on. Overall, you get to describe the liquid phase breaking, cracking of these plastic polymers with a relatively low number of species, 74 or so for polyethylene, about 140 for polypropylene, about 45 for polystyrene. So it's something that is a manageable size still. What are the options so far to estimate rate constants, and what Andrea has been focusing on in his activity? First thing is condensed phase estimates from the literature, which are extremely rare, and I've been dealing with this in a slide or two later on. There are also previous literature models that one could think of. For example, Linda Broadbelt and co-workers are working quite extensively in this area, but these are not available for all polymers. You can make gas phase reaction analogy. We know the chemistry of N and isoalkanes, alkylated and oxygenated aromatics, many other oxygenated molecules. If we take into account the solvation correction, so we transpose that from the gas phase to the liquid phase, and the pillars in these are the free volume theory, Troughton-Meissner rule, we can define reference rate constant and corrections. Corrections from the gas phase and corrections for specific moieties that you may find in a polymer. So, for example, polystyrene will have many different allylic sites that will react completely differently from a normal polymer backbone that has only, let's say, primary and secondary, mostly CH bonds and CC bonds. This correction can be applied also, for example, in the case you want to distinguish between isotactic, bottom left figure, and atactic polypropylene. So we can take these features into account. What I'm showing here is the first level of validation of these semi-detailed chemistry models, where we look at the mass loss profiles from TGA measurements. So we're looking at a very small sample, milligram, pulverized sample of polymer, so no heat and mass transfer limitation. And we basically look at the chemical kinetics of degradation. We can describe the different polymers I mentioned as a function of different heating rates, as a function of different isothermal temperature in the case of isothermal TGA experiments. And most importantly, we can describe the product distribution. So what is the carbon number distribution of unsaturated species? What is the impact of temperature? What is the ratio between paraffins and olefins? What is the total distribution of carbon in terms of carbon number? Then, of course, we can discuss the model is good or bad. There's some deviations if you think about, for example, the C2 and C3 fragments in polyethylene and polypropylene. But at least we get this dependence and in good agreement with the experiments of the product distribution from the operating condition of the pyrolysis process. Polystyrene is known that polystyrene is in principle able to provide the monomer in high yields. And this is a comparison between many different data in our model prediction at different temperatures in isothermal TGA experiment plus gas chromatography and mass spectrometry diagnostics. Why am I getting only a monomer from polystyrene? So if we get back to that radical chain mechanism that I've showed in a general fashion before, and you think about G now being an aromatic ring, phenyl, C6H5, if you do a random scission on polystyrene, you get a radical at this point. This is a resonance stabilized radical that will break by breaking beta scission with this bond. So you have this unzipping reaction that releases a monomer, which is this double bond with the G attached. If you do an H abstraction reaction, let's say you form an high molecular weight mid-chain radical, these undergo beta scission, you form an unsaturated bond on one side, and you form, again, this same radical that I was talking about before on the radical part that you're producing through beta scission. These, again, will undergo unzipping and so on. So basically, nearly all of the steps lead to unzipping phenomena, and unzipping leads to the detachment of one monomer. And this is how you get a large yield of monomers from polystyrene pyrolysis. We can make things more complex approaching the real plastic waste mixers, and then we can look at binary, ternary, quaternary mixtures. And you see the model by just summing up the single decomposition of each polymer. It works pretty nicely if you're considering only polyolefins. And so we can make a prediction of what the product distribution is. Of course, there are some species in carbon numbers that are not represented. This is, of course, due to the lumping approach, and we can look at the feed effect, we can look at the heating rate effect, the temperature effect, and so on. Things are not all good. If in the case we look, for example, at PVC and polyethylene terephthalate pyrolysis, we see something that is very different from what we've seen in previous polyolefins-only mixers. And we're trying to test this issue with Professor Hao Zhang at Zhejiang University in China that is running some ad hoc experiments to solve these riddles we're having with PET, PVC mixtures. So what I'm seeing here in this plot is in points, you see the experimental measurements of PET and PVC mass loss profiles. And in blue, you see the PET, PVC 50-50 mixtures. So if they worked as polyolefins worked, the model would be the solid blue line you see. So it would be a 50% decomposition of one and 50% decomposition on the other. In reality, as you see, once you put PVC and PET together, PET kind of accelerates, and so the mass loss profile curve approaches that of PVC, like PVC is dominating this decomposition. There are studies in the literature where they measure the product from these mixtures, and you actually see clearly that the products are made of monomers of polyethylene terephthalate, so something that resembles terephthalic acids with some chlorinated part. And these clearly indicate some sort of kinetics interaction between one and the other. Similar behaviors are observed for ternary mixtures of PET, polyamide, and PVC, but not, for example, for PVC and polycraporlactone, which is the only one that is miscible with PVC. So is a solubility issue, is a chemical kinetics interaction issue. We're trying to solve this puzzle. We're also trying, together with Francesco Serso, another PhD student in our group, in collaboration with Professor Matteo Salvalaglio at UCL London, increase the accuracy of our rate constant determination. And so we're doing this by using quantum metadynamics approaches, and in particular, differently from the implicit solvent methodology, which is largely, let's say, adopted in the literature, where the liquid environment is assumed as a continuum polarizable medium with no specificity about what is the solid-solvent interaction. In the case of an explicit solvent, we treat the solid and the solvent in two different ways. So we treat the solvent with classical approaches. So each atom is a localized charge, and we treat the solute, so the reactive part of this reactive system, with parameterized quantum mechanics approaches like PM6, which is relatively inaccurate, but it was good to develop the workflow, or tight binding methodology. Then we have to calculate the rate constants. So the rate constant in general of a rare event, if we think about a liquid phase system, we have a huge number of degrees of freedom if we wanted to perform like we do in the gas phase. So do an energy minimization on a stationary point. There will be many different options, and due to the 3n-6 possible degrees of freedom that you have in this system, that you should explore one by one. This is clearly something you cannot do. So you cannot foresee a static calculations that would be very computationally intensive if we want to use these numbers and implement them back in the models I was talking about before. So we use a dynamic approach. This dynamic approach uses a metadynamics approach in the sense that the rare events are sampled by imposing repulsive bias potentials, so by forcing somehow the reactive event to happen. To need so, though, you need to understand a little bit of what the reaction pathways in the polymer formation, so in a polymerization or depolymerization step would be. So what is the reaction coordinate, in other words? In this field, in the field of metadynamics, you impose these bias potentials to make the reacting event faster to occur by highlighting some collective variables. So for example, this is an example Francesco is working on butyrylacrylate, where the two collective variables are the CC bonds between these two carbon atoms and the dihedral angle between these 1, 2, 3, and 4 carbon atoms. Once we've done so, we can determine the flux across a dividing surface by using a rare events transition state theory formulation, where we have two items. One is the free energy change, delta F here, and one is the flux along this dividing surface. So we can identify the potential energy surface as a function of the two collective variables, the CC bond and the dihedral angle. And you can see here the huge difference even in the minimum free energy path between a gas phase channel, the same reaction in vacuum, and the liquid phase channel. So the same reaction in polybutylacrylate. And once you've done so, we can compute the rate constant. This is an example for one single temperature of 400 Kelvin. And you see how our rare events black bar is in good agreement, let's say within a factor of nearly 2, with the measurement by Hutchinson and co-workers on the polymerization rate. This is determined using pulse laser experiments. Secondary gas phase reactivity, the polymer melts, and then the gas phase pieces that are released need to evolve in the gas phase when they have temperature and residence time. We're addressing this issue in a collaboration with the University of Rome Sapienza, and Riccardo Caraccio, which is a new PhD student, is working, has been working during his master's thesis on this topic. So what we're doing here is that what Riccardo did is designing a reactor where a layer of polymer is added on a little, say, boat, that by moving this boat into this flow reactor, he was able to adjust the residence time. Okay, so at different temperatures, you have different residence times, and then he measured and characterized the experimental wax composition and the gas phase species production. This is something that is still in development. The main point in this is, well, first of all, how the model, despite very lumped, so you see this C10, 15, 21, and 30 versus the entire carbon number distribution that you actually experimentally get. But at least you see that by increasing temperature, you are expecting more lower molecular weight fragments. And as you decrease temperature, the fragments you form will be higher. So you will have an higher amount of waxes. So how do we model the system? Not only with a TGA, but we need to feed what comes out from a TGA to a flow reactor model, like in a simplified chemical reactor network, and couple this with the gas phase model to allow for further evolution of the through secondary cracking reactions. And you see here the difference between the experiment and the simulation with only TGA or a TGA plus plug flow reactor, which is, of course, in much better agreement. This collaboration goes on together with Professor De Capraris and De Filippis, also at the University of Rome, La Sapienza. We're also working together with another group in Polimi, expert in LCA and LCA, to couple our understanding of chemistry with the software, with the process software simulators to provide inputs for LCA type of analysis. So, given that we know the chemistry and we can understand the variation of product distribution as a function of the reactor conditions, we can basically generate scenarios to fulfill the requirements of energy and mass balances that people doing LCA needs. So starting from let's say an open smoke based simulation or a chemical reactor network, we provide inputs to the reactors in Aspen-ISIS type of process simulators, and then the mass and material balances are fulfilled for the LCA or ELCA type of analysis by Professor Dotelli and co-workers like Alessandro Salvi and a couple of master students, Costanza and Federica, that worked on these topics. So summarizing on the first example, multi-scale modeling supports the design of solid plastic waste pyrolysis and gasification reactors. There are models that are available, that are developed using a semi-detailed approach. Of course, we're always happy of receiving and having more data to compare with, and we're working now on the coupling with gas phase crack model for secondary cracking reactions. We're also applying this chemistry to multi-scale simulation frameworks, a reduced order, let's say, with the chemical reactor network. There is already and recently published with an application for biomass pyrolysis and gasification. And we're also have available in-house tools for chemistry reduction for using CFD. Example number 2, hydrogen and carbon materials production. Why do we care about turquoise hydrogen? I think everybody of us has understood now that the energy transition is most likely or very strictly connected with the material change, with the material transition. So if we look at the big picture here, and we look at the oil and natural gas reserves that we extract for energy purposes, that is mostly going to energy, and so basically in CO2 emissions, the carbon content in terms of mass is about 80% of this oil plus natural gas fraction. But if you look at the energy content, carbon is 50% and hydrogen is the other 50%. At the moment, we only use a small fraction of these fossil sources to produce usable materials or chemicals, for example, again, plastics. In reality, 90% is only used for energy production, basically through combustion. And another important aspect is that more than 12% of the energy demand is used for the primary metals industry. So the question is, why don't we try to substitute those materials, for example, metals that are very energy intensive, with other materials that we can get from fossil sources contextually to hydrogen? So this is exactly the point of producing turquoise hydrogen. Let's say we take 1 ton of methane. This is worth 55 gigajoule of energy. We provide 4.67 gigajoule of energy to crack methane down to carbon and hydrogen. Overall, this is 38 kilojoules per mole compared to the 63 of steam methane reforming and 286 of water electrolysis. So it's a huge gain in terms of energy duty that is required for a cracking reaction to occur. So you're left with 0.25 ton of hydrogen that still have 35 or so gigajoule of energy. The issue is that, of course, you're producing 0.75 ton of carbon. And of course, you need to find an application to this carbon. And there are many applications. Carbon black is one of the most produced chemicals worldwide. It's about 60 million tons per year, but it's worth only a few thousand USD per ton. But we can foresee producing carbon nanotubes, for example, that have outstanding properties, or carbon fibers for many different applications. And if we achieve this, we are able to lower down the price of hydrogen to prices that are compatible with steam methane reforming, let's say about 2 USD by a kilogram of hydrogen. What is let's say the stakeholders' perspective of this, the legislator perspective? This is not really included in the EU decarbonization plans. This is not green hydrogen. This is not carbon capture and storage, but it is actually carbon fixation into a material that you can use, let's say, quote unquote, forever, or is at least recyclable. We also, I think, have a lexicon issue. You don't want to go and tell to the taxpayer, we are producing carbon. They will be very scared. So here, top left, sorry, of the slide, you see a comparison between the product cost, if you focus on hydrogen. Let's say the target is 2,000 euro per ton of hydrogen, 2 euros per kilogram of hydrogen. And you can compare coal gasification, steam methane reforming, biomass gasification, many other processes for hydrogen production, both on the cost of the product side and on the CO2 footprint side. And you can see methane pyrolysis, in particular, probably is directly connected to renewable electricity through plasma processes. This seems to be quite advantageous process to produce hydrogen. You can do purely thermal methane pyrolysis, a radical chain mechanism, like we all know, or you can do a catalytic type of pyrolysis of methane. So you need a catalyst surface to achieve the production of hydrogen out of carbon. Bottom right, you see what is the typical operating temperatures of non-catalytic pyrolysis, which is, of course, higher, and catalytic pyrolysis by using carbon or iron-based or nickel-based catalyst that, of course, leads to a huge reduction in temperature associated to the lowering of the energy barrier due to the catalytic activity. We've published recently a book on advances in chemical engineering together with Matteo Maestri, with which I'm strongly collaborating with his group in this context. And there are a couple of chapters that I recommend. One is on catalytic and not catalytic chemical kinetics, and one is more on fluid dynamics aspects. There are many reactor technologies that we can foresee for producing hydrogen and carbon. Another question is, are you interested more in the hydrogen or are you interested more in carbon? And this, of course, makes a big difference. So you can think about a conventional flow reactor where you feed methane. This is cracked in a heated zone and you produce hydrogen and carbon. You can think about a fluid wall reactor, because where you want to avoid deposition at the wall that will cause clogging. So you have basically an internal porous wall that allows diffusion of hydrogen from the wall to the inside, but does not allow for diffusion of the particulate matter you're forming to the walls and sticking to the wall, causing reactor clogging. Then you have other type of fluidized bed reactor, which is, let's say, a more or less conventional fluidized bed configuration. Or another interesting aspects we're looking into through the funding from the Ministry of University and Research is a bubbling bed reactor. So in molten metals pyrolysis, where you have a bubble, cracking occurs inside the bubble, carbon is formed, and it floats on top of the metal. Typically, we are using tin, and then you're releasing the gas phase product that are hopefully rich in hydrogen, and you're able to clean up the carbon you're forming at the surface of the metal. This is something every chemical engineer knows, carbon formation in pyrolysis processes. One big example is, of course, steam cracking. And I'm taking this as an analogy. This is something that is particularly historically important in our group, since Professor Dente and Professor Ranzi worked since the early 70s in the area of steam cracking, focusing on coking phenomena in pyrolysis coils. This is something similar if you think about doing this turquoise hydrogen production in a flow reactor. At some point, you need to stop because the reactor will be clogged by the coking phenomena. If you refer to the famous Francis diagram, the only difference somehow is that with steam cracking, we were going from naphtha streams down to olefins, light olefins, ethylene, let's say. Right now, with the turquoise hydrogen and carbon production, we are exploiting all of these favorable thermodynamics, moving from any hydrocarbons in principle or from methane, like in this arrow, down to carbon and hydrogen. Carbon materials applications are various. Carbon black is used as filler and pigment for rubber industry, in tires, paints, and coatings. Carbon nanotubes are finding application in as conductive additive in batteries. So here again, another connection with the electrification of the transportation sector, EMI shielding and other research applications. And graphene is very low production from cracking of hydrocarbons, but is used in flexible electronics typically. There's also another chapter from Juan Villatela and Dea Materials in Madrid that addresses all of these properties and applications of many different carbon materials in the same book that I was mentioning before. So let's start gradually. So we start from the gas phase. Everybody working on soot is familiar with this plot. The only difference is that there's no oxygen in this case, okay? So we start from cracking the fuel, we form the first ring aromatic, we form the precursor, then we get the nanoparticle formation, then we have primary particles formation, and we have aggregation. So we go from the fuel to carbon in principle. So again, here we have reaction classes and rate rules that are extended by analogy from 1 and 2 ring aromatics, from theoretical kinetics in the gas phase that have been done by Luna and Andrea Nobili in our group. We extend these to heterogeneous gas-solid interaction of deposition phenomena, for example, at the reactor wall by DFT-derived correlation, and we have recently published a paper on carbon trends by Francesco Serse. Everybody's probably familiar with the approach, discrete section approach to soot modeling. Of course, we cannot pretend we are tracking each single particle. So taking the particle size distribution function, we define pseudospecies that we call bin. We then assign H to C ratio that varies to stand for the soot maturity. We use a uniform spacing factor of 2. So we go from 20 carbon number in 25 pseudospecies up to 10 to the 8 carbon numbers, which stands for a spherical equivalent particle of 200 nanometers. In the context of other collaboration with other industries, Andrea has extended this to higher diameters, I believe up to 400 nanometers. So we get the heavy PIHs, we get the soot particles, we get the soot aggregates to describe the same process that I was describing in this previous slide. Of course, if we think about turquoise hydrogen production, we have gas phase reactivity, we have soot formation, we have deposition on the walls. So we need to validate this gradually. Let's say we need to look at the gas phase while taking into account PIHs and soot formation. We need to look at the PIHs formation, of course, taking into account soot formation and, of course, deposition phenomena. And then we can look at the deposition phenomena once we have everything else validated. In other words, we're trying to close the material balance, the carbon balance, that it is not easy to close probably experimentally. At least the model can provide some closure to this carbon balance. So we can look and make predictions based on the pressure effect, temperature effect, residence time effect. We can look at all of the different intermediates. Acetylene has an important role, of course, in turquoise hydrogen production, and of course, a safety related, some safety related issues. Acetylene is quite explosive. Acetylene pyrolysis is exothermic. If you look back at the Francis diagram, it will show up clearly. And then based on this parametric analysis of different reactor condition and the effect on products in the gas phase, we can also look at the volume fraction. We can look at the number density. We can look at the mean diameter of the particles as a function of all of the variables. So we've extended this to describe chemical vapor deposition phenomena. So the reactions are basically the same that lead to the growth of soot particles starting from aromatics and pHs and so on. So we get the ACA mechanism, we have radical recombination, we have resonance stabilized radical roll and recombination, we have cyclization reaction. This leads to the growth of the solid phase. This is an example of the deposition rate experiments from Lacroix and co-workers. This work is our recent paper, and you can see here the impact of just including soot formation. Again, back on the carbon balance example I was telling about before. We're also again working with the University of Rome La Sapienza in the production of turquoise hydrogen and carbon material. And again, this is a comparison between our model and some methane conversion as a function of different residence time or flows into this quartz reactor. The mole fraction of hydrogen formation as a function of temperature. We were able also to identify and quantify some aromatics, again, a comparison between model and experiments. And then we started to look at the effect of deposition, different thickness of deposition on the reactor walls on the conversion of methane. This is, of course, helpful to understand how and when you should stop the reactor from operation, make some cleaning, and restart again. We're also, of course, trying to characterize the carbon that we're forming. In this case, you see some SEM images on the left side of the homogeneous phase formed carbon, on the right side of the deposited carbon on the surface of the reactor. We've applied this to chemical vapor deposition processes. So you have a substrate and you want to grow a carbon material that has different properties as a function of the pyrolysis severity. You can produce either smooth laminar, rough laminar carbon. They have different tomographic properties. And for the applications, for example, of production of car disc brakes, of course, there's also a, let's say, property chemical structure relation to be drawn to understand what is the best carbon you want to produce to have that specific mechanical or thermal properties for braking devices. In this area, we're again working with Matteo Maestri work, and in particular, this is the activity of Clarissa Giudici, another PhD student in the group. We started off from an existing surface chemistry model from Lacroix and co-worker that I mentioned before, but that model was entirely based on analogy with benzene and did not predict the formation of anything else that perfectly aromatic six-member ring surface, so graphene-like structures. In reality, if you look at the potential energy surface that is constructed in this work by Clarissa that we're about to submit, this is done using a PBED3 functional with periodic plane waves boundary condition. Of course, we're focusing on, I believe, 50 carbon atom cell, not on an entire graphene layer. But you see that many pathways give access to something that is not exactly a carbon bulk graphene-like, but has some moiety that have a different reactivity, or even a five-member ring. A five-member ring, everybody knows from PH's chemistry, when you start to form a five-member ring, you start a curvature, and that's, of course, has an impact on mechanical properties and other properties as well. The aim of exploring this potential energy surface is, one, to define rate constant for the heterogeneous gas-solid reactions using clumping image nudge elastic band, but also to find shortcut ways to determine those rate constants. So if I know the gas phase analogy, and this example refers to a work from Michael Franklak and co-workers on 4-phenanthrenyl plus acetylene potential energy surface, we can draw some sort of Bell-Evan-Polanyi plot, and maybe then if we know the barrier in a gas phase reaction through which for which we can adopt very accurate method, we can then transfer it to the gas solid reaction equivalent by applying a correction to the energy barrier and to the, of course, to the entropy factors. And the point is describing as nanostructural features and defects in a robust but easy to use and relatively small in size kinetic mechanism. This is actually the challenge. This is a few comparison between deposition rates and deposited mass in chemical vapor deposition and infiltration experiments. And here you can see if we define a defect as the ratio of 5-member ring, for example, we're still working on this, but you can see how this defect form and grow and decrease as a function of the operating condition. Most importantly, we can also predict the composition between soot formation and deposited carbon. Of course, in chemical vapor infiltration reactors, for example, if you form soot, at some point you will have clogging, and again, you have to start off to shut down a reactor and restart again after cleaning. So we have actually applied this to Brembo production of car disc brakes. This is a CFD simulation by Professor Alberto Cuoci. We can predict quite nicely the bulk density. Clearly, you can see that given a long infiltration time, we're talking about days, you can see the first part, which is a typical chemical regime trend, so linear with time, and then at some point, mass diffusion limitation comes in. We can provide inputs on which reactions are important. If we know something about the preform that you're using to densify these carbon materials, and we know the surface to volume ratio as a function of the porosity, we can also predict their impact on the bulk density in infiltration processes. Final step is extending this to a catalytic process. A catalytic process that we want to use in the context of carbonab to produce nanotubes. So we have typically a catalyst precursor, ferrocene, that is sprayed into a flow reactor that is called floating catalyst chemical vapor deposition reactor. It starts to nucleate and provides the active sites, catalytic sites, for the carbon to deposit and to grow in the form of nanotubes. And in the end, believe me or not, but it's actually is a thing, you can actually spin out the carbon nanotubes from the bottom of the reactor like they were, air, okay? The literature proposes a pentagonal-based ring mechanism, and Clarissa adopted this. Then we can, of course, eventually talk about chirality. We need to consider chirality, but this is just a first, let's say, development in terms of framework and infrastructure to being able to model such processes. But in reality, the quality of a nanotube is based on, is defined by the aspect ratio, so the length over the diameter. And the diameter when the catalyst is sprayed in is strictly dependent on what the diameter of the catalyst is. So you will have a distribution of diameter, and therefore you will have a distribution of aspect ratios and diameters of the carbon nanotubes. And so we apply the same discrete section approach that we applied to soot, but to describe the distribution of diameters of nanotubes that is basically resembling the distribution of the catalyst particle diameters. So we can grow in many different ways, starting from the pentagon. We form this first N1 pseudospecies. This N1 pseudospecies at one point, through the formation of a 5-member ring, will close on top of the catalyst particle like a table, and then the carbon that is attached to the catalyst then will only be used to grow the nanotube in length. And so based on the different diameter, we can cover the description of the chemistry. Unfortunately, there are not many data available in this. At present, Clarissa is working in Madrid with Juan Villatela to get more data. The data I'm showing here are from another partner in the Carbonab consortium, which is Professor Adam Boyes at Cambridge University. So once we have the temperature profile inside the reactor, we have the surface to volume ratio of the catalyst that is derived from particle size measurements of the catalyst entering the reactor. We can start to make prediction. You can see here the evolution of our pseudospecies that I described before. And here on the bottom left, you can see the comparison between our model and the experimental data by Adam Boyes and co-workers, which is in relatively good agreement. Again, this is probably the only data set we can simulate at the moment. Again, you can look at the competition between nanotubes growth and soot. Of course, you want to maximize the conversion of carbon from the feedstock into nanotubes rather than amorphous carbon in this case. All right, so turquoise hydrogen, concluding, is a feasible and promising midterm solution to sustain the foreseen hydrogen demand. the cost of hydrogen and let's say the sustainability of this pathway largely depend on the value of the carbon material you are producing. And this is what our research is focusing on. We do have multi-scale reactor modeling tools that we are developing. We are making efforts to describe nanostructural features and defects. We are also planning on extension to plasma reactors. We are now addressing, as I said, wall catalytic effects for the production of hydrogen, for example, at your house. Okay, so you get methane, you crack it down into hydrogen, and you can use hydrogen as a feedstock for your energy duties, domestic energy duties. We are performing hierarchical validation of strongly interconnected subsets, gas, PAHs, soot, surface carbon, nanotubes. They all exist together, let's say, in this system. We have a scarcity of validation experiments. So this is, again, another call for new experiments. And we are at least helping, supporting the experimentalists also to closing the carbon balance. Some of you may argue that this may not be let's say, a sustainable or a relevant pathway in decarbonization, but this actually could be carbon negative. The only thing that needs to change is that you're not using methane or natural gas anymore, but you're using maybe biomethane, biogas that you get from waste biomass feedstocks, and then you're producing hydrogen and recyclable carbon materials while basically acting as a carbon negative process. With this, I'd like to thank you very much. I hope I was more or less in time. I think I was slightly ahead, and I'm happy to take any question from you.
Thank you very much for this very nice talk. Very forward-looking presentation. I was looking forward to that, and I'm very happy that I mean, you met my expectation. Thank you very much, Matteo. So if there is time, as Matteo was mentioning, for questions, is there any question from the audience? While people think about it, I have a curiosity. So you have actually pointed out that this is a field where there is not much data. And so you actually called for experiments and data to validate models. But so my question would be, what is the level of confidence we have today in the models that you have developed? Is it possible to assess this confidence? Is there such a thing like high fidelity simulations for the processes that you have presented? Because of course the lack of data is a major problem. Thank you.
Maybe first thing is that the lack of data was, let's say, strictly related to chemical kinetics relevant data. So the first comment. No, I would not define this as a process where high fidelity models are available. We are working in that direction by co-developing, let's say, the kinetics part and the reactor simulations part. This part is more on the catalysis group, but no, I wouldn't say you can make predictions right now on details like the aspect ratio of carbon nanotubes. You can maybe get the mass that you are converting into some sort of carbon, right, at the moment, and the hydrogen contextually, or other intermediates and products in the gas phase. But no, there's not such a level of detail. There's something more on the CVD and CVI processes. A big school in France, Vignoles, Lacroix, and many other people. In that case, we do have some kinetic significant data that we are using. Yes.
Thank you. So I don't know. I know that Marco is raising his hand.
Ciao, Marco.
But we can't hear you at the moment.
Okay, I was mute. Ciao, Matteo.
Ciao, Marco.
Thank you, and sorry for my voice, but my nose is a bit clogged. Too much wind yesterday. No, I had a curiosity about, because to what I know, in the crack model, the species carbon is a gaseous species, right?
Yes.
So how do you okay, for example, if there is something like a boudoir equilibrium in this process that you, so what is from CO2 you produce solid carbon. How can you simulate this with considering it as a gaseous species?
Yeah, you're perfectly right on this. Let's say the big difference between turquoise hydrogen and soot is that in soot, hopefully you're forming ppms. In this case, you're forming 0.75% of mass. So even the mass flow in the gas phase will change dramatically. And the reason why we consider gas phase species in the soot mechanism is that it's just ppm, so it does not impact much the gas flow through the reactor. In the context of some industrial collaboration, we are actually we are addressing these aspects by considering the variation of the mass flow due to the formation of carbons. And something that we've already done is to make the thermodynamic of the soot formation mechanism consistent by looking at graphene thermodynamics to make some equilibrium prediction. This was again in the context of another industry collaboration, and so we are addressing these topics. One, thermodynamics has been already addressed. The variation in mass in the flow is being addressed. Yes.
Yeah. Thank you. It was just this.
Thank you, Marco. I see that Salvatore has raised hand. Yeah.
Yeah. Thank you, Matteo, for this interesting presentation, interesting talk. I was wondering how far are you from integrating these kinetic models into CFD simulations? Like, or do we have to stick? Either we have to stick with lumped mechanism and perform CFD simulation, or the other way around is to do like a reduced representation of flow condition, like with the chemical reactor network, and then we use this detail mechanism that you presented. Is there a good compromise that we are reaching, or are we there yet, or there's still
that's
work to do?
It's a far-looking question. I think there's a bit of both. As you know, I'm not a big expert in CFD, but people in the group are working to use the plastic models in CFD simulations. There's two ways you can do this, either by strongly lumping or reducing with the methods we all know, or you can use the detailed chemistry to come up with some few steps mechanism that has the stoichiometric coefficient, let's say, of the products, and you can use them in the CFD by strongly reducing the number of species. That's one other approach we're looking into in the area of mostly of fire safety, so to use some strongly reduced chemistry model. The other side, which is the one I like more, but just because I like to see what the chemistry is the chemical reactor network. The point of junction in these is something we are pursuing together with Darmstadt University, which is deriving automatically from CFD computations what the equivalent reactor network should be of that reactor, and then use that reactor with detailed chemistry. So to be honest, I think it makes sense at the moment to, of course, pursue both pathways.
Thanks. Thank you.
See a question.
Thank you very much. I see Panos as a question. Thank you, Panos.
Hello, Prof. Hello, Matteo. Thank you very much for the presentation.
You're welcome.
I don't have an expertise in combustion at all, nor SFD. So I will go in a question more to my part, which is related with the energy and climate policies. You mentioned yourself in some point that when you were describing the process, that it's not the best regarding circularity. So because next week, that's a coincidence probably they will revise again the regulation on the use of plastic and specifically on waste and packaging direction. They will change it a lot. I don't know if you are following. There is most probably they will ban forever the single-use plastics. and all of them will be reusable. So since you mentioned it already yourself, can you elaborate more on that? I mean, are you planning to change it according to the new regulations, or what else you can add on that part? I'm interested. Thank you.
Yeah, on the plastic side. So I think there needs to be a connection between people doing science and legislator, but there are some things that as a researcher, you're pretending you're doing for the sake of science, not dependent on legislation and regulation. I'm saying this because what we're learning from the plastics pyrolysis, and what would be very important in the upcoming year, provided or not that single-use plastic will be forbidden or not. I think this will be still a great topic, because in the end you are reusing a fossil source over and over again. This is the possibility. The implication of what we're developing in terms of chemistry models in that area is also of high relevance in polymerization processes. So even in the context of producing biopolymers or targeted polymers for specific applications, or intelligently designed polymers and so on. I'm referring to, for example, at the part where I talked mostly about more molecular dynamics aspects of rate constant calculations. All that we are getting in this area, the experimental information we're getting in this area, are coming from the polymers community. And so I believe, independently on the single plastics, I believe chemical recycling has some advantages that mechanical recycling does not have. And nonetheless, the frameworks we're developing will be still applicable in polymerization, so still in the context of circularity somehow.
Okay, thank you very much.
Thank you, Panos, for the question.
Thank you. I think I don't see any raised hand anymore, so I will take the chance to thank again Matteo, Professor Pelucchi, for having accepted our invitation, and thank you, Matteo, again. Get well soon.
Thank you, everybody. Thanks for organizing.
Thank you.
And everybody for participating, of course. Thank you.
And of course, for all the others, we meet for the next appointment. That would be
next week.
Next week.
Next Wednesday, Friday.
Okay, thank you. Have a nice weekend.
Thank you. Bye-bye. Have a nice weekend.
Bye-bye.
Bye-bye.